Okay, I forgot to do this, so sorry, you kind of needed this in order to do the more harder problems. Equivalent resistance, equivalent capacitance, really easy. We just use my equation. The equivalent capacitance is the 1 over C1 plus 1 over C2 inverse. So let me plug in my numbers. So it's 1 over 4 plus 1 over 8 inverse. And 1/4 plus 1/8 is 3/8, so it's 8/3. So 8/3 times 10 to the minus 6th, which is what, 2 2/3 or something like that? Yeah, 2 2/3, so 2.67 times 10 to the minus 6th, or times 10 to the 6th, times 10 to the minus 6. Oh, my brain just broke. Times 10 to the positive 6? No, minus 6. Farads. Okay, so that's my equivalent capacitance. Now, how do you find the charge stored on each capacitor? Well, first, this is a series circuit, so you need to remember in series that the like equivalent charge. This is like a weird statement, but imagine equivalent capacitance means we take this thing, and this circuit behaves the same if there's one capacitor with a capacitance of 2.67 times 10 to the minus 6 farads. So the equivalent charge is equal to the charge of each capacitor, Q1, Q2. They're all the same. And so I'm going to find this equivalent charge with this equivalent capacitance and using the voltage of 12 volts in my definition of voltage. So again, the definition of capacitance is Q over delta V. So that means that Q is equal to C delta V. In this case, the capacitance, my equivalent capacitance, is the 2.67 times 10 to the minus 6th. And my voltage is 12 volts. 12 times 3 is, 12 times a third is 4. 4 times 8 is 24. So we get 24 times 10 to the minus 6th coulombs is my charge stored on each capacitor. So that's equal to Q1 and it's equal to Q2. They both have the same amount of charge stored on them. Potential difference across each capacitor. So in series, we found out that the potential difference across the battery is equal to the potential differences added together. So they're not the same, so I have to do a little bit more math. But I'm still going to use this formula. So this formula tells me that the potential difference across the capacitor is equal to Q over C. And so for 1, the potential difference across 1 is equal to Q, which is this, 24 times 10 to the minus 6th. Over C, and the capacitance for 1 is 4 times 10 to the minus 6th. So this equals 6 volts. And I can do the same for 2. So delta V2 is Q over C, which is 24 times 10 to the minus 6th. Over the capacitance, which is 8 times 10 to the minus 6th. And that is going to be equal to 3 volts. The problem could have also asked you, what's the potential difference across the battery? Ah, poop, I made a mistake somewhere. Okay, I found my mistake. This shouldn't be 24. 12 times this is 32. Sorry about that. And I'm using a pen. So these should be 32s. And 32 divided by 4 is 8. 32 divided by 8 is 4. And so we get 8 volts for the first voltage, 4 volts for the second. How do I know I made a mistake? These two have to add up the potential difference across the battery, which is 12 volts. So that's how I knew I made a mistake. Sorry about that. Okay, next one. Equivalent capacitance in parallel, super easy. You just add the two together, which is 4 plus 8. 4 times 10 to the minus 6 plus 8 times 10 to the minus 6. Should probably put parentheses here. Which is 12 times 10 to the minus 6 farads. The charge stored by each capacitor. How should I do that? Well, I'm going to use this equation again, that the capacitance is Q over delta V. And I'm actually going to do C first, I guess. I know the potential difference across each capacitor, because the potential difference across the battery is equal to the potential difference across 1, which is equal to the potential difference across 2, which is 12 volts. They're all the same. And so for the charge, I'm going to multiply C and delta V, and my delta V is going to be 12 volts. So Q1 is going to be C1, which is 4 times 10 to the minus 6th, times 12, which is 48 times 10 to the minus 6th. That's Q1. Coulombs. Q2 is the same idea. 8 times 10 to the minus 6 is the capacitance. The voltage is still 12 volts because we're in parallel. 12 times 8 is 96. Times 10 to the minus 6 coulombs. That's Q2. You'll notice that the bigger capacitor stores more charge if the potential difference is the same, which I think makes sense conceptually. You could have also solved this with proportions if you wanted to. Like this one has twice as much capacitance as this one, and so this one should store twice as much charge. You could have done that and then use equivalent capacitance to do that. That could have worked too, but I use this method. But anyway, those are the answers. Bye.